We're going to talk about how to graph cube root functions. So the cube root function is the inverse of the cubic function. So let's complete the table to graph the cube root parent function f of x equals the cubed root of x. So what we're going to do is we're going to plug in these x values and figure out the points we need to create this graph. So if we start off with f of negative 8, that is the cubed root of negative 8, which is negative 2. Then we have f of negative 1, which is the cubed root of negative 1, which is negative 1. Then we have f of 0, which is the cubed root of 0, so that's 0. And then we have f of 1, which is the cubed root of 1, so that's 1. And then we have f of 8, which is the cubed root of 8, so that is 2. So let's go ahead and plot these points. So negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, 2. And so we can connect these points to form the graph of the cube root parent function. So I have a little bit better picture of the graph on this slide. So that you can see here, this is the graph of the cube root parent function. So some key characteristics we'll describe when we're talking about cube root functions are the domain and range and the intercepts of the function. So remember, the domain is all possible x values of a function. The range is all possible y values of a function. So some key characteristics we can describe about this function are the domain and range. There are no restrictions on the cube root. Cube root always exists. It doesn't matter if we have negative numbers, positive numbers, fractions, decimals, anything will work. So the domain will be all numbers from negative infinity to infinity, which is the same thing as saying negative infinity is less than x, less than infinity. The range is going to be all values from negative infinity to infinity. So we can say the range is negative infinity less than y less than infinity. So the intercepts will occur anywhere the graph crosses or intersects the axes. So we have x-intercepts where the graph crosses the x-axis. So you can see here in this graph it has x-intercepts at negative 1, 0, 2, 0, and 4, 0. Y-intercepts are where the graph crosses or intersects the y-axis. So we have a y-intercept at 0, 8. So let's describe the intercepts of this cube root function. So it has an x-intercept right here at negative 1, 0, and it has a y-intercept right here. So I'm going to approximate the location of that point. That is at 0, and then let's say about 0.25. So now we can talk about local maxima and minima of the function. So a function will have a local maximum at a point, such as A, if that point is larger than the other y-coordinates around that point. So it's not necessarily the highest point on the whole entire graph, it's just higher than the other points in that region. Similarly, we have a minimum, like this value here at B. That is a local minimum because it's lower than the other y values that are around it, but it's not necessarily the lowest point on the whole entire graph. So when we're talking about maxima and minima of a cube root function, we're going to look at a specific interval. So if we look at the interval from negative 4 to 4, I'm just going to draw in these boundary lines, we can look for the minimum and maximum y values, right? Remember, minima and maxima refer to the y values. So the lowest y value is going to be right here. So the minimum is going to be negative 2 at x equals negative 4. And then it'll have a maximum y value of 1 at x equals positive 4. So now let's look at this cube root function and describe its key features. So the domain is going to be from negative infinity to infinity because cube roots have no restrictions. And then that's going to be the same thing with the range. The x-intercept will be right here at negative 8, 0. The y-intercept will be here at the point 0, 2. So on the interval from negative 9, okay, so let me draw in those boundaries, negative 9 to 0, let's think about the maximum and minimum values of the function. So it'll have a minimum value, you can see the lowest point is right here, so it'll have a minimum of negative 1 at x equals negative 9, and it will have a maximum value right here of 2 at x equals 0. So now you can go ahead and pause the video and try this example on your own. So once again, the domain and range are going to both be from negative infinity to positive infinity. The x-intercept is right here at negative 1, 0. The y-intercept will be here at 0, 1. On the interval from negative 2 to 0, you can see I've drawn in the boundary lines. It's going to have a minimum value of negative 1 at x equals negative 2. It'll have a maximum value of positive 1 at x equals 0. So now what we can do is we can graph a cube root function using its key attributes. You can determine the domain and range, determine the x-intercepts and the y-intercept, any local maxima or minima, and then plot some additional points. So let's try graphing this function f of x equals the cubed root of x minus 1 plus 2. So let's start off with the domain and range. So since it is a cube root function, it's going to have no restrictions on its domain and range. So the domain will be from negative infinity to infinity, and the range will be from negative infinity to infinity as well. The x-intercepts will be where y equals 0, right? X-intercepts have the form x0, so we're going to go and plug in 0 for y. Remember that f of x is y, so we have 0 equals the cubed root of x minus 1 plus 2. So now we need to solve this equation for x. So this is like what we did in the previous lesson when we were solving cube root equations. So we're going to isolate the radical, right? Subtract 2 from both sides. So I have negative 2 equals the cubed root of x minus 1. I'm going to undo that cube root by raising both sides to the third power. So that gives me negative 8 equals x minus 1. So now I need to solve for x, and I'm going to do that by adding 1 to both sides. So when I add 1 to both sides, I get negative 7 equals x. So that means that I have an x-intercept at negative 7, 0. So now we need to figure out the y-intercept of the function. Remember, the y-intercept is found by figuring out f of 0. So I'm going to go to my function and plug in 0 for x. So we have 0 minus 1 plus 2. So we have the cubed root of 0 minus 1, that's negative 1 plus 2. So the cubed root of negative 1 is negative 1, so we have negative 1 plus 2, and so that equals 1. So we have a y-intercept at 0, 1. So what we're going to do now is we're going to go to our grid and plot these 2 points on there. So we have negative 7, 0, and we also have our y-intercept at 0, 1. So we're going to plot that there. So now we need some additional points. I think at this point it's really helpful to go to Desmos and to enter this equation into Desmos. So you can do that by clicking this keypad, and then we're going to go to functions to find the cubed root. Okay, you're going to need to scroll all the way down until it says nth root, which is right here. So the nth root, and then you can see the cursor is on the index. So you just enter 3 for the cubed root, and you click down here, and then you're going to do x minus 1. And then we need to click out of the cube root so we can do the plus 2 on the outside. Okay, so we have the cubed root of x minus 1 plus 2. So now we're just going to find some points on here that we can use to fill in our graph. So for example, I see that it has, let's see, it crosses here at negative 7, 0. So beyond that we have like a point, let's say negative 9, negative 0.1. So we can plot that on our grid. We have negative 9, negative 0.1, so that's going to be here. Let's look for some values between negative 7 and x equals 0. So let's see, we have negative 2 and then 0.5. So we have negative 2, 0.5. The more points that you plot, it'll be better for you to approximate the shape of the graph. So I can fill in this part I have right here. It's going to go like this. Connect these points. Okay, and then we're going to plot some additional points. So at 1, we have 1, 2, which is another point on our graph. So we're going to go ahead and plot that. So we have 1, 2, and then we have, let's see, at 2, we have 2, 3 on our graph. So 2, 3, so it kind of goes up like this, and then to 2. And then beyond 2, 3, let's pick a point. Let's see, 5, 3.5 up here. And so the graph just goes on like this. So, you know, you can kind of approximate what the cube root function looks like with the help of Desmos. So now you can go ahead and pause the video and try graphing this function on your own. So when you graph this, the domain and range are once again going to be from -infinity to +infinity. The x-intercept will occur where you set the function equal to 0 and solve for x. So when you do that, you'll get 7 equals x, so it has an x-intercept at 7, 0. The y-intercept can be found by doing f of 0. So when you do f of 0, you'll find that it has a y-intercept at 0, -1. And then you can go to Desmos and once again enter this in Desmos. Just to remind you, you go to the keypad and then functions, scroll down to the nth root, and we have the cubed root of, let's see, x minus 8 plus 1. So you go under the cubed root, x minus 8, and then click out, and then do plus 1. And then you can get some additional points that you can use to graph this function. So you can sketch the graph, which kind of looks like this, using Desmos. So remember, when you're analyzing graphs of cube root functions, make sure to pay attention to some key characteristics. You want to think about the domain and range and any intercepts of the function.